Everyone, so I am going to virtually present our poster with the title Improving Reasoning in Vision Language Models by Perception Verified Self Training, which is accepted at ECCV 2026. So, if I come to motivation first, so firstly, I will give you a brief introduction about what the self training is. Okay, so in the self training, we have a data set with image, quotient, and a ground truth or golden answer, and we have a weak model. Okay, our task is to make weak model better at reasoning. So if we directly train it on the ground truth answer, golden answer, it won't make its reasoning better, right? So we need a rational or reasoning data set. Now, we don't want to generate it from a higher end or costly or proprietary models, right? So in self training, we generate the responses or rational data set from the weak model, and we train the same weak model on its own responses. Okay, so that is what a self training is. Now the process is we basically prompt the weak model with the image and quotient, and we ask it to generate a reasoning followed by a predicted answer based on the reasoning. Okay. Now, if the predicted answer is correct in the sense it matches with the golden answer present in the data set, we say that okay, the reasoning is good, and we basically incorporate that entire rational sample into our training data set. Okay, we generate the training data set for the entire domain, and we then train the weak model, the same weak model, on its own generated response or its own generated training set. Okay, then after training we get a model which is better at reasoning. Then we basically do the same process. We again we use this basically better reasoning model and again generate the rational data set or training data set. And since it is generated with a better reasoning model as compared to the previous iteration, the data set is better. And if we train the weak model with the base weak model uh, with this new or better data set, then we'll get a more better model. So iteratively we will get a more and more better reasoning model through self-training. Okay. Now we have analyzed the existing self-training methods and we have observed two failure modes. One is the visual hallucination, where the rational with it generate with which it generates, right? It contains non-existing visual features. Means it contains details which are non-existing in the original image. So here you can see in the example, blue jar is there, right, which is present in the model output. Now blue jar is nowhere in the image. We have blue particles, green particles, white jars, but blue jar is not there. So these are visually hallucinated details which are present in the reasoning. And second is the language shortcut, means basically it relies on its textual priors to generate the reasoning instead of seeing the image and grounding its reasoning based on the image. So these are the two failure modes that we observed, and these are because of the same reason we analyzed. This reason is, I have told you, right, we need to judge whether the generated rational are correct or not in order to incorporate into the training data set. So the judgment is based on the final answer correctness. It generates reasoning, and on the basis of reasoning, it generated the final predicted answer. If the final predicted answer is correct, we can say, okay, the entire rational quality is good. But what happens is, basically we can have noisy details which are present in the reasoning, and still we can have the final predicted answer is correct. So in this way, we incorporate that noisy reasoning sample in as part of our rational data set, and we trained the model on that set, making it making its output also noisy. Okay, then we use the same noisy output model to generate another training set, and hence basically we will get more and more noisy uh, more noisy output generated by the subsequent iteration models. Okay, so we need to remove we need to basically correct the process. Okay, so for correcting the process, first thing is we need to judge whether the visual details which are present in the reasoning sample is correct or not. We cannot do this if we are not able to isolate this perception part with the reasoning part. Okay, so firstly we leverage a prompt template. What it will do, it will isolate the perception part or the caption part of the model output with its reasoning part. Okay, so now our rational contains three component. One is the caption component, followed by the reasoning component and the predicted answer. The caption is nothing but the perception part of the image. Reasoning is based on the perception part, and then we have the final predicted answer which is based on the reasoning part. Okay. So we have basically isolated the caption part. Now we can judge whether the caption is correct or not, or whether it contains hallucinated details or not. Okay. Uh, this will we do via PerceptEval, which we propose as an unsupervised dual alignment framework. And since now the reasoning is based on the validated caption part, we say that the language shortcut problem is now eliminated. Why? Because what the language shortcut is, model relies on a textual prior rather than true visual grounding. Okay, since we are firstly prompting the model to have the perception cleared, then followed by reasoning, we say the reasoning is based on the caption details which are validated, right? So the language shortcut problem is also eventually removed from this. So the thing is, firstly we come to our perceptual part. So okay, to in order to judge the caption, we need ground truth captions, right? But as I told you, in our data set, the only thing which we have ground truth is the golden answers. So in order to judge whether the caption is correct or not, or whether the model correctly understood the image or not, we propose PerceptEval, which is an unsupervised dual alignment framework. So we observed the images and we saw two things. Like every image has two things. One is the text embedded inside it. So here in the image you can see mass of the particle, average particle speed. All these are text, right? So there are two things. One is the text and another is the visual details. Visual details is nothing but the jars, the particle colors and all, particle size, particle colors. So all these are visual details, and there are text details. Okay, so we need to have our generated caption align with both the text details or OCR details as well as the visual details. So in order to check whether the caption aligns with the OCR details or not, we propose a method to validate it. Firstly, we basically there is a package by the name of Paddle OCR. It is a lightweight package. We generate the OCR of the image through this Paddle OCR package, and so now we have OCR of the image and we have the predicted caption. Okay, we use sentence transformer to generate the embeddings of both this Paddle OCR text, Paddle OCR text, as well as our generated caption. Okay, and then we use cosine similarity to check whether these two embeddings are similar or not. And if these two embeddings are similar, we say okay, the caption contains details about the OCR of present in the image, or the caption is in alignment with the OCR which is present in the image. We check whether, so after cosine similarity we get a threshold. We check whether we get a value which through a threshold we check whether this value is greater than a given threshold, and if it is greater we say okay, sufficient OCR details are present in the image, present in the caption. Now, in order to check whether the generated caption aligns with the visual details or not, we use FG-clip. FG-clip is similar to clip. In clip, it takes input image and a short phrase about the image, and it generates a score. Okay, the score generated is whether the short phrase aligns with the image or not. Okay. Now in FG clip, instead of a short phrase, we can give a long caption also. So it is nothing but checking whether the long phrase is in alignment with the image or not. So it checks whether the visual details present in the mentioned in the predicted caption aligns with the image or not. Okay. So in this way, it gives a score, and we can basically check whether the score is greater than some threshold or not. If it is greater than some threshold, we can say okay, the predicted captions is in accordance with the visual details present in the image. Okay. So now we have validated the caption part, right? We have validated the caption contains enough details, enough OCR details as well as enough visual details which are present in the image. And we can say, okay, the caption part is validated. Now, there is one more thing, which is the threshold thing, right? In order to check whether the OCR part is greater than some threshold, or the visual details present in the predicted caption is greater than some threshold, we need to define thresholds, right? This threshold we define based on the domain. Suppose a domain is having only text heavy images, right? So then its OCR component should match perfectly as compared to its visual components, right? So then we will have a higher end threshold for OCR component, and we have a like lower end threshold for visual details. So likewise, suppose there are some domains where which is fully heavy with visual details and OCR is very less, and it won't matter also, right? It won't matter much to basically have the OCR in the predicted caption. So we can have the OCR part, OCR threshold at lower end and visual threshold at higher end. So this is how, based on domain, we can adapt our thresholds, and hence our perceptual caption validation step. Now, a rational is validated only when both its caption and final answer are correct, right? So we have validated the caption. Even if the final answer is also correct, it means that the caption is correct. Based on the caption, we have the reasoning, and the final answer is correct, right? So the reasoning is based on the correct visual details. And if the final answer is also correct, we can say the reasoning is correct, right? So if the caption part is correct, if the final answer is correct, we can say mostly that reasoning will also be correct, and hence the entire rational will be correct. And we incorporate this entire rational into our training data set. Now we have proposed our curriculum self-training framework. So in the stage one, like other self-training methods, we train the model on its own generated or its own generated and validated rationals, right? So earlier the validation method was based on the final answer correctness. Here in our proposed case, it is based on uh, the final answer as well as the validated caption. Okay, so we perform self-training until the performance saturates. Now we also introduce stage two self-training. Okay, so in the stage one, we have trained on the validated rationals. Now in stage two, we introduce model to more difficult samples. Okay, so what we discarded in step one, we have discarded all those samples for which the perception is correct and final answer is incorrect, right? Because we say, okay, the final answer is incorrect means the reasoning was incorrect. Now we on our analysis we found out that the reasoning is incorrect because it is not based on the visual details which are highlighted in the caption. Okay, so in order to have the correct reasoning, we need to force the model to explicitly have its reasoning based on the correct caption, right? So that's why we proposed a caption guided reasoning enhancement. So as part of stage two, we prompt the model with the image quotient and the correct caption it has generated for a given sample, and then we force the model to generate reasoning based on the caption which is present as part of a prompt. Then the model generates reasoning and the predicted answer. And if the predicted answer matches with the correct answer, we incorporate the sample in our training data set. The sample will be like correct caption, correct reasoning, followed by the correct answer. Okay. So in the second stage, we will have validated rationals as well as the rationals which are generated through caption guided reasoning enhancement. So in the second stage, it is more like we are introducing somewhat difficult samples to our model, right? To our training pipeline. So the model will become more better as compared to only performing the stage one. So this is how what our curriculum self-training is. And in the third column, we have mentioned the quantitative results. Okay. So we have presented many quantitative results in our basically research paper, and some of them we have incorporated here. So the first is the main table. In the main table, we have compared our method with existing baselines on across different domains of M3 core datasets. So we have domains like language science, common sense, natural science, social science. Okay, and for zero shot methods, basically we have for zero shot methods or baseline, basically we have shown the results on different prompting methods. For direct SFT means like directly tuning the model on only the ground truth or golden answers, and self-training methods is basically improving the reasoning of the model through different self-training methods. We have basically officially we have performed the official implementation of star and R3 to present their results. As you can see, our method has performed the best across all the domains and across all the other baselines. All these results are basically uh, carried on Lava V 1.57 billion model. Okay. And then we present two outer domain distribution results. So basically for the first result, we have trained the models on the language science dataset, language science domain of M3 core dataset. And then after self-training it on LS domain, we presented the results on the OCR domain of hallucinations, right? So language science is nothing but text-heavy images, and the OCR domain of hallucinations also have text-heavy images. So this is a kind of out of distribution result. For the second table, we have used the models which are trained on the natural science domain, and we have presented their results on the science domain of triple MU. So in both the tables, you can see our method has performed the best across all the other baselines. The third graph is basically there we have performed an ablation study on two domains, language science and common sense. So instead of performing the two-stage curriculum self-training, we can all do all this in one step only. Like from the very starting only, we can accommodate the difficult samples, right? But as you can see, initially the accuracy is better. Uh, you can see the accuracy is better in doing everything as part of a single stage. But eventually it will saturate early, right? Otherwise, by doing in with our curriculum self-training framework, initially we train only on the validated rationals until the performance saturates, and then we introduce the difficult sample. So you can see the performance is far better as compared to having training or introducing difficult sample from the first step only or from the stage one only, right? So this is validated as part of both language science domain and common sense domain, and this is why we have adopted for curriculum self training instead of introducing the difficult samples without giving model any confidence from the first step only. Okay. So this is what about our research work. And if you have any doubt, you can mail me or any of my co-authors, or you can have your doubts in the comment section. We will try to address this as soon as possible. Yeah. Thank you for listening.